Is that better? Seems like it might be. Okay. What I was going to say is I wanted to thank the previous presenters this morning because they've actually covered quite a lot of the background to what I'm going to talk about here about testing large buildings. I also want to say thank you to Colin Olson, who's sitting right here. Give everyone a wave, Colin. Colin works at the Energy Conservatory, and they've done a lot of work on trying to develop test methods. And you're going to see pictures of Colin in this presentation. And I might even ask Colin to answer your skill testing questions later, because unlike me, Colin has done a lot of this work. And so, Colin, you got to pay attention. I might be asking you things. Okay. No. There we go. So I think, like I said, I think we covered a lot of the sort of background and introductory material already about, why would we test large buildings? Historically, we have not done so. But, if we want to care about energy use and moisture use and so on, we probably want to control those envelope airflows. And I think the last bullet there about assessing construction quality, I think that has also been at the back of people's minds, sort of independent of controlling these airflows. And Valerie made comments about some of the metrics we use and the units we use. So I've tried to be inclusive here using cubic meters per hour or liters per second or cubic feet per minute. All of those are acceptable, I hope. And often we're going to normalize these results by some sort of area. When we're talking about airtightness here, it's going to be usually the envelope area of the building in square meters or square feet. And I wanted to give just a couple of examples we have in the US, the standards that say this is the tightness level we want you to reach. And the ASHRAE 90.1 energy standard says 7 cubic meters per hour per square meter. But if you want to do better than that, there are things like green construction codes that go down to something like half that. So why are large buildings different from other buildings when we are testing them? And I wanted to pick out just a few key differences. One is this idea that you want to have the same pressures everywhere when you're testing, but with a big building, that is hard. If we just imagine the building we are in today, so many floors, each floor is very large. If you wanted to push all the air that's going to go out through the exterior envelope down the one corridor that's outside this room, that would be a big airflow resistance. There's no way you would pressurize the whole building just by blowing air into that corridor. And then there's issues with what happens on a windy day. Taller buildings get a lot higher wind pressures on them simply because they are taller, and wind speed increases as we go away from the ground. So the top of this building, it's much windier than if we were testing a single-story building. So we also have stack effects that depend on the temperature difference between inside and outside. Again, they are much bigger for taller buildings. You have to move a lot of air when you're testing a big building. The sort of equipment that we've used a lot for residential and some smaller buildings, one of those fans is not going to be enough. You're going to need lots of them. That requires a lot of coordination. Or there have been some attempts to use one really, really big fan, but they are hard to transport, hard to power, lots of issues. Then there's things like safety issues. It can be a very noisy process when you're moving a lot of air. You have issues with slamming doors, for example. That's another safety issue, particularly if the building is occupied. What about fire doors in buildings? Probably we have to open them all for testing, right? But that can be tricky to get permission to do that. So you have to coordinate with whoever is in charge of the building from a fire control perspective. And then there's the crazy things that occupants do. You need to control the whole envelope. So if you have openable windows, you can't have any of the windows open while you're testing. And you have to make sure that everybody in the building knows that. Same with interior doors that might have to be open. Everyone in the building has to comply with that. And that could be a challenge, particularly in a bigger building with hundreds of people in it. And finally, big buildings get big HVAC systems that could move a lot of air. And if you can't control the operation of that building HVAC system, you can't control the building pressures, and you won't be able to do your testing. And there's a challenge there of having complete control over the HVAC system while you're doing the testing. There are a few test methods that exists for leak air tightness testing. And I wanted to just point out just a few things where these might be introducing challenges. And Valerie touched on some of these already. For example, they often have requirements for the maximum amount of pressure variation within a building. For example, ISO 9972 says you've got to be within 10%. That might be hard in a big building. Things like the lowest measuring point that you use has to be 5 times the natural pressure. That's the pressure you measure before you've turned any fans on. Well, if it's a windy day or a cold or a hot day and you've got lots of stack effect, that natural pressure might be a big number. And then the pressures you have to test at get exponentially larger, right? It makes it very, very challenging. The ASTM test method has requirements for only a 5% variation in interior pressure differences. Again, that can be hard to achieve, right? It has an interesting limit in it where you multiply the height of the building by the temperature difference, and we end up with very strange meters per K units or meters per degree C, but the ASTM method restricts that to a maximum of 200. That's easily exceeded in a large building, as you might imagine, right? Just a couple more points here, and then I'll move on. There's issues about should you test at multiple points or single points, and then our friends at Passive House who really like tight envelopes a lot, right? No one tightens an envelope like people building to Passive House standards. They say, well, maybe we don't have to follow these test methods, and we can come up with some other requirements of our own that might help out. And I have an illustration to show this in a moment about we should definitely try to make sure that we have at least the same sign of pressure on all the building surfaces, for example. And if I go to the next slide here, this is just an example illustration that I actually took out of the Passive House manual to sort of illustrate this. And I'll step through this a little bit. The green arrow at the bottom is the pressure that got measured before any fans were turned on to pressurize or depressurize the building, something like 35 pascals. That was from the wind and the stack effect. So even before we get started, there are bits of the building with 35 pascals pressure across them. So in order to get all the leaks having the same sign of pressure, we're going to have to get to at least another 35 pascals, right? And that's the yellow points that you see here. So here's the building getting pressurized, but we don't have the same sign of the pressure, either positive or negative across all the leaks, until we get up to about here, the first of the red dots. And so you can see we're going to have to move a lot of air and get to big pressures on some parts of the building. At the other end of the scale, we have the issue of if you follow the standards, they often require a minimum number of points over a minimum range of pressures. Well, then you end up here where you need very, very big building pressures in some cases. So this is sort of illustrating some of those points I talked about for what do the current test standards say, and why might that be a problem for big buildings. But there are some ideas about how we might get around this, right? We could use many fans in different locations. That might make it easier to get uniform pressures. To be sure that you have that, you could measure pressures at multiple locations in the building. You could wait for good weather, a not windy day, a day where it's not hot or cold. You could test when buildings are unoccupied, so that you don't have occupants opening and closing doors and windows, turning fans on and off, and so on. And also we could be a little bit smarter about how we test and probably automate some of this. And if you have questions about how to automate, we might get into that in the discussion later. I'm sure Colin will be happy to answer your questions. It's a challenge, but doable, right? To coordinate all those pressure sensors and all those fans. So now I'm just going to spend the next 10 minutes or so talking about a couple of examples, because I think it might be easiest to do this by example. These were 3 tall buildings in Austria, side by side. You know, they're not the same, right? They're all subtly different, so they have some different characteristics. And they're different heights. They have basements. They have different volumes. They have different exterior surface areas. But we're probably going to apply similar principles to testing all of them. You know, one question is, I mentioned you could install fans in multiple locations, but where would you install them and how many do you need? When we're testing tall buildings, we need to do a lot more preparation, if you will, in advance of the testing to answer questions like, how many fans will I need and where should I put them? And we can have estimates of, in this case, they estimated they would need 18 fans to pressurize this building. Where might you put them? You have to find floors where you can locate these fans, where they can exchange air with outside. That's not necessarily trivial. Obviously, on the ground floor, there's often doors in buildings, in fact, almost always, which are great places to put them. But when you're at the top of the building or in the middle, not so easy. I'm assuming, Colin, you had to do things like find mechanical rooms and things like that for this? Balconies, okay. Thanks, Colin. And then there's questions that you might want to try and answer in advance of testing about, how uniform is that pressure difference? The solid red building there is the ideal one, right? We got 50 pascals everywhere all the time. But is that realistic? So in this case, they did some pre-testing before the test, where they went out on a winter day. It was minus 1.5 degrees C outside, plus 20 inside. You've got a building 125 meters high. We're talking about pressures in excess of 50 pascals across the building all over before we even start. And trying to make that uniform is not trivial. There's also a lot of work for building preparation. Things like you need to keep all the exterior openings closed. Doors and windows we're kind of familiar with. You need to make sure that the plumbing systems in buildings, particularly when they are new and have not been used, that you actually fill up the P-traps with water and put a little bit of water in the toilets and the showers and so on. These big buildings often have ventilation systems, and if you have dampers to control outdoor air, you need to have them closed. Otherwise, when you pressurize, you might just be measuring the outdoor air damper. Similarly, for fire control, right? There are often dampers in ducts for fire control, and you have to figure out, are they going to be open or closed? And then you've got to make sure all the doors stay open all the time. And in this particular case, they needed 1,200 door wedges that somebody had to go and install. Right, that's not a trivial thing. And then we need to deliberately set up interior airflow paths. And in this case, the illustration here is for using a lift shaft. The lift shaft is convenient because it tends to connect a lot of floors, and it's a relatively large hole that traverses the building. But then you have to think about, well, who's going to make sure all those doors are open and are safe, for example, because we don't want people falling down lift shafts. So this introduces a whole another area of safety when we are testing that maybe for smaller buildings we're not so concerned about. You can measure pressures at multiple locations. In this case, you can measure at the top, ground floor, and somewhere in the middle, and that lets you assess how uniform your pressures have become during the testing. And I'm going to, assuming all of that went well, and eventually in this building, they were able to test it. And I just wanted to share some of the test results so you get a sort of a feel for the magnitude of the flows we are talking about. Something like 60 to 80,000 cubic meters per hour. So we had to move a lot of air. I gave you the metrics in terms of air change rate and air permeability. These are taken right out of the AIVC paper that I have a reference for later. So, but this is just to give you a feel for how much air we have to move. It's a lot, right? It is a tremendous challenge. The second example I'm going to give was from this is from an ASHRAE research project that Colin participated in. I just wanted to have at least one picture here that shows there's a lot of things you have to manage when you're operating multiple fans and many pressure measurements. There's a lot of tubing, a lot of wiring. You're going to need some sort of computer and software control to manage this and record the data. And in other words, you're not just going to go out there with a simple manometer and do this testing. In this study, they went to 16 different buildings, between 4 and 14 stories, between 7,000, 24,000 square meters. So quite a variety of buildings. Some were offices, some university buildings, and so on. And a modified ASTM test method was used with multiple fans. And here you can see a few of the fans in some doorways. Another tricky thing is, wow, sometimes big buildings are complicated. This is a floor plan here, how it changes between the 10th floor and the first floor. The little red circles are examples of where you could put a fan. But these buildings are complex. They're complex shapes. They're complicated inside. They have many different rooms and so on. And when you test, you have to control all of that somehow. All of those doors, all of those rooms have to be controlled. There is the possibility, of course, of not bringing fans with you because these big buildings have fans in them. You could use the HVAC system. Again, there's questions about how well can you control that system in such a way just to do testing. This study, they also found that it wasn't obvious what the exterior area of a building is. It's not trivial to measure. What if it's a strange shape? If you just have flat sides and it's a rectangle, okay. But it turns out that's kind of rare, actually. And how do you measure that area to do that normalization to know if you've met the standard is an interesting challenge. And they found some variation, up to 15% variation in how different people estimated the exterior surface area. This idea of measuring in multiple locations, maybe we don't have to do that, right? It could be okay to measure at one location or maybe at the middle as well if we're careful about what we do. Then there's questions about, what counts, what doesn't count. Is a mechanical room with does that count as part of the building, or should that be outside the envelope? In other words, when the building is normally operating, is that space supposed to be inside or outside? Because that determines the pressure boundary you're trying to test. And you need to have some rationale for deciding if those spaces are inside and outside. And lastly, when we ventilate buildings, it means we've got holes between inside and outside, part of the HVAC system. We'd better know how the dampers function. Like, you can't trust what we call a gravity damper. So this is a damper that doesn't have a mechanical fan attached to it. It just operates with counterweights and things like that. And these are some of the results from all those buildings that were tested. And I'm going to apologize to Valerie for using CFM 75 per square foot, but the point here is not necessarily that precise number. It's that it changes a lot from building to building. And I think that's important, because if all these buildings uniformly tested low and there's little variation, we might say, well, we're just building great buildings and we don't have to test them. This tells us that we do have to test these big buildings to see if they're going to comply, because maybe they do, maybe they don't. There's a lot of variability. There's also some differences between pressurizing the building and depressurizing, which we have seen for all kinds of buildings that have been tested. This is a common thing, that there's often a 10 to 15% difference between pressurizing and depressurizing, because when we change the direction of airflow through the leaks, not all leaks are rigid, right? And they can have some valving action in them. So that's not unusual. So just to finish up here with a few recommendations about, if we're going to test big buildings, what might be some good ideas. We almost certainly are going to have to use multiple fans in multiple locations in order to get uniform pressures. We need to be careful about what happens due to the stack and wind effects on the building that changes the baseline pressure, because we want to make sure we at least have the same direction of airflow through all the leaks. It's a good idea to test both pressurization and depressurization. If you're trying to predict airflows under natural conditions, all of our experience with other testing says we should do both, but again, that could be a challenge. And probably the biggest determinant of, do you get a quote unquote good test result, and are your results repeatable, is this issue about being very careful about preparing the envelope and the HVAC system, controlling the occupants, and so on. But from the Austrian study, they had a few ideas about, that limit of 200 meters Kelvin that I quoted from the ASTM test method. Maybe we could relax that for taller buildings and use a higher number. I don't see a right or a wrong here. This is something our community needs to debate, right? They had recommendations about, maybe you could take some weather information about wind speeds and only test at low wind speeds, and maybe limit the testing to times when it's not too big a temperature difference between indoors and outdoors. And like I mentioned at the top of this presentation, I wouldn't be here saying this if great people hadn't put a lot of effort to measuring stuff. Colin is here in the room with us today, but also several folks in Austria wrote a great paper. You can read it in the AIVC proceedings. I highly recommend that you do so. And so I want to thank those people for, if I may say, pioneering efforts in this field. And I'll stop there. And I don't know if we have time for comments or questions, just with a few examples, some more historical than others, about airtightness testing. Thank you.
Thank you very much, Ian. We do have time for 1 or 2 questions now. So any questions? Yes, no.
Arnold, please.
Yeah.
Well, when I see all of this, I think it's crazy. What an effort. So I was thinking, is there experience with doing things otherwise, not pressurizing the whole building, but compartmentalizing, trying to do some floors, or the floors where you expect the main infiltration to take place, ground floor, top floor.
Right.
Is it easier or not? You still have the internal partitions that then should be sealed or kept at a zero pressure difference.
Well, Arnold, I'm going to talk about that later today, about internal partitions and their leakage from a multifamily perspective. But yes, I assume it's possible. I don't know of any studies. I'm looking at Colin to see, do you know of any work where people have tried to do parts of a building, then add it up?
I would generally try to avoid that if possible. There are some cases where that is not possible. There are phased occupancy buildings where the lower floors are already being occupied while the upper floors are still being built. That's one reason why you may need to test what we sometimes call pancake testing, floors at a time. And also in extreme temperature, inside outside temperature differences, your stack effect might be just too large if you try to test an entire tall building. That's another reason to test in slabs. The problem with the slabs, as you pointed out, is shafts for plumbing and electrical need to be controlled, or you'll overestimate the leakage. The good news is if you're able to pass that test, it's a conservative estimate because you know you've missed some of the leaks.
Yeah, I think that's a good point, Colin. If you're aiming to just pass or fail some building regulation, it's trickier if you want to use that number to say, use it in an energy model to estimate the airflows, right? And then those pancake tests, they're almost always going to overestimate that leakage. But I think you're right, Colin. If you're just trying to test the, do you meet some leakage level? Sure. Oh, Valerie?
Yeah, I was to say that we are doing a lot of pancake in France, and this is usually the way we test high-rise building. We test the top floor, the bottom floor, and something in the middle. And in fact, it's supposed to be airtight between floors according to the fire regulation in France. So if it's not tight because of plumbing, too bad for them. It should be. So no matter. That's yeah. So we don't care that there is internal leakage. There should not be anyway. So we don't account for them, and it's taken in the energy performance calculations, and they take into account this value. The main problem is with the elevator that cannot be tight, and sometimes they just try to tight the elevator door, seal it and perform the test by sealing the elevator doors to avoid the leakage through the elevator. My question for you was then, what is your recommendation? What should be put in the standards to test high-rise building? What would you remove and add in ISO 9972 standards to test high-rise building?
I think, Valerie, we should have some discussions about things like the weather. Like, should we be more relaxed about multiplying the height by the temperature difference? And then have some other requirements in terms of how do we better account for the pressures that you get at the beginning of the test when the fans are off, and how they combine, as we know, how they combine sort of non-linearly with the rest of the test, and figure out, do some more thinking about that. Like maybe we can allow some bigger offset pressures at the beginning of the test, but change our calculation procedures to maybe account for that in a better way. you will still have non-uniform pressures. And because we have a non-linear pressure flow relationship, that's always going to be a challenge, right? But maybe we can just make, you know, some conservative assumptions and say, if you are testing just to meet an air leakage limit and you're not going to use this to estimate airflows, then we could have a path you could take where we'd have some conservative estimates to linearize the problem and account for the offset pressures. So I think there are things we can do, because I think you're making good points earlier about if a regulation requires you to test, you need a test that people can use, right? We can't have regulations that require you to do things you cannot do. So we're going to have to do something. And I think the compromises will be made, but I think we can make informed compromises based on, you know, some of the work that people are doing, where we're learning more about how to test these buildings. I think right now it would be good to have more information, more results from testing large buildings, but I think we can get a start. Is that helpful? Okay.
Thank you. So considering the time, let's continue and see if any questions in the later